Hey physics students, Mr. Presenters here. I'm on page 240. This is chapter 7, and what we're talking about is Newton's law of universal gravitation. Right? All bodies, if they have mass, have a gravitational force. We can't feel it because our gravitational force between you and me is so small compared to the gravitational force between us and the Earth. So Newton's formula is the force of gravity equals big G. Big G is a constant. I'll give you that in just 1 minute. Big G times the mass of one object times the mass of a second object divided by the radius squared. So big G, as promised, equals 6.673 times 10 to the negative 11 Newton meters squared divided by kilograms squared. All right? So it's an extremely small number. It's an extremely small number, as you can see. What I do want to point out is the relationship between radius and the force. The change in gravitational force follows the inverse square law, and what that basically means is this: that if you have force at 100%, I just drew a small grid here. Here's 50%, 25%, and this is distance. Okay, and that would be our radius down here. You should be able to recognize the inverse square plot. The further we get away, the longer the distance, the less the force. The force keeps going down. All right? Now, what's interesting is the force doesn't go all the way to zero. We just reduce it. We keep reducing it, and we're all familiar with the satellites that geosynchronously rotate our Earth, and what and there's also there's a way for you to understand how these satellites get up there. Is that if we're able to launch them, here's the Earth. If we're able to launch them, and then they're able to get far enough away that the gravitational force is less than their forward force, then they could still be moving, but not quite have enough force to fall, but continue to move in an orbit. But they still have a small amount of gravity. Same with the astronauts. The astronauts still have a small amount of gravity, but it's a very, very small amount inside their capsule as they are in the spaceships that are within our orbit. So the gravitational force keeps going down and down until finally, if you're far enough away, of course, you could reduce it to zero, but chances are it would pick up again at another planet. But what I want to do is practice this equation, and if we could practice this equation, we could do that using practice C on page 242. We have planet your mass of the planet, radius, and it's important to recognize it's the radius from the center of mass to center of mass. All right, so if we were determining the radius, we would find the center of the mass. That's what we're interested in, the distance. Right? Just the distance between these two bodies as they're in their rotation, and it's from the middle of the body to the middle of the body. So even if you wanted to calculate the gravitational pull, you would have to start from the center of the Earth to whatever geosynchronous satellite you're referring to. All right, so it's not from the edge of the Earth; it's from the middle. All right, and then force of gravity. All right, so we could do this for 3 planets: Earth, Mars, and Pluto. This happens to be number 3, I believe. If you look, it says number 3. Okay, so we'll use a mass of 66.5, and all these are in kilograms. And the mass of Earth, which can be found on a table, is 5.97 times 10 to the 24th, and these are in kilograms. Mars is 6.24 times 10 to the 23rd. These are in kilograms. 1.25 times 10 to the 22nd is the mass of Pluto. And the radius is in meters. 6.36 times 10 to the 6th. 3.40 times 10 to the 6th. And 1.2 times 10 to the 6th meters. Alright? Now, the force of gravity, the way you would find that is that we could start with Earth. So the force of gravity, and we're starting with Earth, equals big G with which is our constant, 6.67 times 10 to the negative 11 times 66.5, which is your mass, and that's in kilograms, times 5.97 times 10 to the 24th, divided by the distance, which is 6.36 times 10 to the 6th meters, but remember that's squared. Alright? And that would be 651 newtons. Alright? And so we could do the same thing for Mars. So the force of gravity on Mars equals the constant. This is a universal constant, which is 6.67 times 10 to the negative 11 times your mass, which is 66.5, times the mass of Mars, which is 6.42 times 10 to the 23rd, divided by the distance, which is 3.40 times 10 to the 6th meter, and that quantity is squared, and that's 246 newtons. Alright? And then Pluto, we would calculate the same thing. Force of gravity on Pluto equals big G, which is 6.67 times 10 to the negative 11 times your mass, which is 66.5, times the mass of Pluto, which is 1.25 times 10 to the 22nd, divided by the distance, which is 1.2 times 10 to the 6th meters, and that quantity is squared, and it's 385 newtons. Right?